Welcome to IT.Solution, your total network, system, firewall, and security partner.
Welcome to this explainer on SRWE Module 3. Today, we're going to take some standard networking concepts and completely transform them into a fun, structured journey to understand virtual LANs or VLANs. Look, if you're studying for your CCNA, or you're out there managing real enterprise networks, you already know that keeping traffic organized and secure is absolutely essential. So today, we're rolling up our sleeves to unlock the mechanics of Layer 2 segmentation. Okay, let's dive right in. I want you to picture the pure, unadulterated chaos of a massive, unsegmented network broadcast domain. Imagine trying to teach 5 different classes, say history, math, science, art, and gym, in one giant, totally wall-less room. How crazy would that be? I mean, you wouldn't even be able to hear yourself think. Well, in the networking world, when all your devices plug into a switch without VLANs, they form exactly that, one massive broadcast domain. Every broadcast packet, every multicast or unknown unicast just gets flooded to every single port. It's incredibly inefficient, it's a security nightmare, and honestly, it's a massive drain on your network's performance. So to fix that, here's our roadmap for today. We're going to demystify the VLAN, explore exactly why we use them, break down the different types, explain 802.1q tagging, look at trunks, and then prove it all in the CLI. Let's kick things off with Section 1, demystifying the VLAN and building those virtual walls. The absolute crucial takeaway here is that a VLAN acts like a Layer 2 virtual wall. It logically separates groups of devices so their broadcast noise is totally isolated. Think about it. Instead of buying a separate physical piece of hardware for the math class and a totally different one for the science class, your switch configuration just places each port into a specific VLAN. The switch's forwarding logic simply refuses to forward frames from a port in one VLAN out to a port in another. So they physically live on the exact same box, but logically, they're in completely different networks. Moving right along to Section 2, why use VLANs? What are the actual technical benefits? Segmenting your network actively upgrades your infrastructure in 4 huge ways. First off, smaller broadcast domains. This shrinks your failure domain right down. Next, we get massively improved security. This ensures that only users in the same VLAN can talk directly at Layer 2. So if you've got a VLAN for faculty and another for students, they literally cannot cross over natively without hitting a router or a firewall first. Then, of course, there's reduced cost. You're allowing one physical switch to do the job of many, which saves thousands in hardware. And finally, better overall performance. You are dramatically cutting down the CPU overhead on every end device and eliminating bandwidth waste from those nasty broadcast storms. All right, Section 3. Let's look at understanding VLAN types, or as I like to call it, the flavors of segmentation. So we basically have 4 main flavors to configure. Now, while VLAN 1 is the default right out of the box, best practice tells us we absolutely need to assign data, native, and management tasks to other dedicated VLANs. First up is that default VLAN, VLAN 1. Every single port on a brand new Cisco switch sits here. You can't rename it, and you definitely can't delete it. Second is the data VLAN. This is where your standard user-generated traffic goes, things like email and web browsing. Third, we have the native VLAN, which is strictly used on trunk links for untagged frames, usually for backward compatibility with older tech. And fourth, the management VLAN. This is an SVI, or Switched Virtual Interface. It's basically a virtual IP for the switch itself, used purely for remote administration like SSH. Trust me on this, you never ever want your end-user data mixing with your switch management traffic. Let's dive deeper with Section 4, 802.1q tagging explained, taking a microscopic view. If we compare a standard Ethernet frame to an 802.1q tagged frame, the big difference is basically a temporary passport. It's a tag inserted right into the data so the switch knows exactly which VLAN it belongs to. A normal frame has your destination MAC, source MAC, type and length, data, and finally the frame check sequence or FCS. But the 802.1q frame, it explicitly jams a 4-byte header right in there after the source MAC address. And the real magic is happening inside that 4-byte tag, specifically in the 12-bit VLAN ID field. That ID is the exact number identifying the network. And because it's 12 bits long, it mathematically allows for up to 4,096 distinct VLANs on a single network. Pretty wild, right? You'll also notice the switch has to recalculate the frame check sequence at the very end. Because we literally changed the size and content of the frame by injecting this tag, the old FCS is totally invalid. When the frame eventually leaves the switch to go to a PC, the switch just rips the tag back out and recalculates the FCS to normal so the PC is blissfully unaware it was ever even part of a VLAN. Section 5 brings us to trunks and multi-switching. Think of these as the hallways between our switches. So VLANs are the walls of our classrooms. Trunk links are the hallways connecting them across completely different buildings. A single point-to-point 802.1q trunk link can carry tag traffic for multiple VLANs at the exact same time between physical switches, like VLANs 1, 2, and 3 just cruising together. These trunks act as the super conduit, keeping all the data logically separated by relying on those 12-bit tags we were just talking about. Simultaneously, it allows the native VLAN to travel down that same hallway completely untagged. Both sides of the trunk just have to agree on what that native VLAN is. So if a switch receives an untagged frame on a trunk, it immediately knows exactly which network to drop it into.
Finally, Section 6. Let's look at configuring and verifying VLANs and get some proof in the CLI.
To build that trunking hallway, we have to jump into interface configuration mode. By using the command switch port mode trunk, we are forcefully telling that link to carry all our active VLAN traffic. We're overriding the default behavior, essentially telling the port, hey, you're no longer just a single-lane road for one device, you are now a multi-lane highway for switch-to-switch communication. We're also throwing in switch port no negotiate, which turns off dynamic trunking protocol just to lock the interface down securely.
Now, to verify all that actually worked, the show interfaces switch port command gives us the rock-solid proof we need. It clearly shows the operational mode is trunk, the encapsulation is .1q, and that trunking VLANs enabled is set to all. It even confirms our trunking native mode VLAN is set to 1 by default. This right here is exactly how you prove your commands took effect on the hardware.
And for the final piece of the puzzle, the show VLAN brief command proves exactly what our Layer 2 landscape looks like. It confirms that our default VLAN 1 is active, and it lists every single access port assigned to it. You can also see those legacy default VLANs from 10.02 to 10.05 sitting there, the ones you can't delete. If we had spun up a dedicated data VLAN, its ports would be nicely organized and verified right alongside it.
So I want to leave you with this. Take a hard look at your own environments. Are your broadcast domains properly segregated with dedicated data, voice, and management VLANs? Are your trunks securely passing tagged frames between switches? Or are you still trying to operate in that chaotic, wall-less room? Take these concepts, go build your virtual walls, and take absolute control of your network architecture. Thanks so much for joining me on this explainer, and I'll catch you next time.
Thank you for watching. See you in the next episode.